Welcome to this JAX crash course. If you do something with deep learning or any scientific computing in Python, you should definitely learn about JAX because it can significantly speed up your code and has lots of other great features. I mean, just look at this first example where we compare normal NumPy and then JAX NumPy. And when we look at the execution times, then we see JAX is over 100 times faster in this example. So this is super cool. And today I show you what JAX is. Then we go over all the essential things we can do with it. And in the end, we also talk about why we cannot use JAX everywhere and where we have to be careful with it. So let's get started. All right, so first let's have a quick look at what we discussed today. So first we have a look at what JAX is. Then we do a little speed comparison. Then we learn how we can replace it for NumPy. And then we have a look at the 4 essential functions. So we learn how we can speed up computations with JIT. We learn how we can do automatic differentiation with grad, automatic vectorization with vmap, and automatic parallelization with pmap. And then I also show you a short example training loop with JAX, so how this could look like. Then we also discuss what's the catch, so where we have to be careful and why we cannot use it everywhere. And then we have a short summary in the end. So let's get started. So first of all, what is JAX? JAX is developed by Google and it is AutoGrad and XLA brought together for high performance numerical computing and machine learning research. It provides composable transformations of Python and NumPy programs. So with this we can differentiate, vectorize, parallelize, and we can do just-in-time compilation. So in simpler words, JAX is NumPy on steroids, or it's NumPy on the CPU, GPU, and TPU, but it's actually much more than that. So we can, for example, also get automatic differentiation. And this is super helpful if you do anything with deep learning or scientific computing. So now let's have a quick look at what is XLA. So if we go to the link, we actually land on the TensorFlow website. And by the way, I put the link to this Google Colab in the description, so you find this below the video. So XLA stands for Accelerated Linear Algebra, and this is the foundation what makes JAX so powerful. It's also developed by Google and it is a domain-specific graph-based just-in-time compiler for linear algebra. So you don't have to understand what this means in detail. You just have to know that this is the underlying foundation and this significantly improves execution speed and lowers memory usage by fusing low-level operations. So we have a more detailed look at this just-in-time compiler in a few moments. Now, first of all, let's do a simple speed comparison. So here we have a simple NumPy code where we have a simple function that does this computation. And then we put in a NumPy array and time this. So now if we run this, then NumPy doesn't have GPU support. So this is actually run on the CPU. And in a few moments, we hopefully should see how long this takes. All right, so here we have it. So this one was the fastest execution. And now let's have a look at the same code in NumPy. So we also have JAX NumPy, which is basically the same as normal NumPy, but the JAX implementation. But the API is very similar, so almost identical. And then we can also use this JIT. So this is the just-in-time compiler. And with this, we can transform the function to be just-in-time compiled. And then we can also transform the NumPy array to a JAX NumPy array. And now if we run the same code, but with JAX, then this is significantly faster. So in this case, I'm also running it on the CPU, but we see that already this brought a much better performance. And by the way, we use this block until ready because JAX uses asynchronous execution. So be aware of this. And now let's actually change the runtime to a GPU in Google Colab. And then let's run this again and then have a look at the performance with GPU support. All right, and now we see we get this execution time, so only 3.74 milliseconds. So this is a significant performance boost. So this time NumPy was also a little bit faster, but still this is almost over 100 times faster, which is huge. So now let's learn how we can use JAX NumPy as a drop-in replacement for NumPy. So one use case is to use JAX as a drop-in replacement for NumPy, and then we get GPU support. And this often works without problems because the API is almost identical. So let's have a quick look at this. So here we have a simple code with NumPy where we use a few functions. So we use linspace, and then here we use the NumPy sinus and cosinus. And then we plot this with matplotlib. And now let's have a look at the same code with JAX NumPy. So we import JAX NumPy as J and P. And then these functions are actually the very same, so the very same API, but here we use JAX NumPy, and then we can use linspace, sinus, and cosinus. And if we run this, then we get the same plot, so it basically has the same values now. And yeah, so this is how we can use this as a drop-in replacement, and this alone will get you a great performance boost because then we can have GPU and TPU support. The only very big difference that we have to be aware of is that JAX arrays are actually immutable, and we talk more about why this is the case in a moment. But yeah, be aware that JAX arrays are immutable. So if we have a look at this code with a NumPy array, where we create an array and then we change one of the values, then this works. But if we do the same with a JAX NumPy array and run this, then we actually get a type error. So here it says object does not support item assignment. So JAX arrays are immutable, so be aware of this. And now the next thing we have a look at is JIT. So how we can speed up our computations with JIT. So JIT, or also known as just-in-time compilation, is a method of executing code that lies between interpretation and ahead-of-time compilation. So ahead-of-time is, for example, what we could get with C++. And with just-in-time compilation, we compile the code when we run this the first time. So at runtime, it is compiled into a fast executable. So the first time, this can be a little bit slower, but the next time this is cached. And then the compiled code is much faster than just normal Python code. And it works by using this JIT function. So we import this from JAX. So I already did this up here. So we say from JAX import JIT. And then, for example, we can apply this to function. So this is also known as a function transformation. So here we have a normal function that does some computation. And then here again, I time this with a normal NumPy array. Then here I time this with a JAX NumPy array. And then here we simply apply this JIT function to this function, and then we call this JITted, and then we can also call this as a function, and we put in the JAX NumPy array and then also compare this. So if we run this, then let's wait a few moments and then let's have a look at the results. So this is the normal NumPy execution. This is with a JAX NumPy array on the GPU, and this is as a JITted version. So this is the fastest of all, and this is how we can get this huge performance boost. So we could use it this way by just applying the JIT function and then put in the function as argument. Or we can use this as a decorator. So we can decorate a function with @JIT. And now this has the same effect. So again, if we run this, we get a very fast execution time. And now let's have a look at how this works. So chit and other JAX transforms work by tracing a function to determine its effect on inputs of a specific shape and type. So this tracing here is very important, and let's look at an example. So here we have a function that we decorated with add chit. And then here we do a few print statements, and then we do a operation in here. So this is a JAX NumPy dot product, and then we return the result. Then here we create two NumPy arrays. So let's run this cell. And now let's run this cell and call the function and see what we get. And notice that here we don't see the print statements, but rather than printing the data, we print it prints the tracer objects that stand in for them. And when we run this function again, then we actually no longer see these tracer objects, but only the output, which is again the same as in the first run. So it's the same result, but now we no longer need these tracer. We only need this the very first time. And these tracer objects are what JAX chit uses to extract the sequence of operations specified by the function. So basic tracers are stand-ins that encode the shape and data type of the arrays, but they are agnostic to the values. So this is also very important, and I will come back to this again in a moment. So it's agnostic to the values. And now this recorded sequence of computations can then be efficiently applied within XLA to new inputs with the same shape and data type without having to re-execute the Python code. And this is also why we no longer see these objects in the second run. So this is roughly how chit works. So now let's have a quick look at a few limitations of chit. So this is also very important, why we cannot simply use chit everywhere and speed up everything in our code. So this sentence here is very important because chit compilation is done without information on the content of the array. Control flow statements in the function cannot depend on traced values. So like I said before, it is agnostic to the values. So a function like this cannot be chitted. So here we have a control flow statement, a if statement that depends on the value of x. If x is greater than 0, we return this, and otherwise this. So now if we try to apply chit to this function and run this, then we get a very long and mysterious error. So here it says concretization type error. Abstract tracer value encountered where concrete value is expected. So this might sound confusing, but basically you just have to know this. You can't use control flow statements that depend on the value. So be very careful with this. And now to make this chit work, you have to implement a so-called pure function. So let's quickly have a look at what does it mean to be a pure function. So for this, again, I recommend reading this part of the JAX documentation about pure functions. But basically, it means that you can't have control flow statements that depend on the values, like I just showed you. Then it cannot use or change global states, so only variables inside the function and not outside of its scope. So we can't use global variables. So we cannot use them, we cannot access them, and we also cannot change them. Then we cannot have an I/O stream, so no printing, asking for input, or accessing the time. And we cannot have a mutable function as argument. So these points here are very important to keep in mind. If you want to apply this chit just-in-time compiler, then be very careful to implement pure functions, because otherwise this is very dangerous, because then you can have untracked side effects. So it can change the results of your computation without you knowing about this. And this can be super dangerous if it changes the result. So yeah, be very careful to make sure to understand how chit works and how you implement pure functions so that you can apply chit. Because once you know this, then this is super powerful to speed up your code like I showed you before. But again, be aware of these side effects. Now let's look at another great feature of JAX, and this is automatic differentiation with grad. So most people only know JAX for the NumPy on the GPU or for this just-in-time compiler, but this is actually another very powerful feature, especially for scientific computing or deep learning. So with this, we can very simply calculate gradients or second or third order gradients and so on. And the difference between JAX grad and deep learning libraries is that here it follows more the underlying math rather than using backpropagation. And this can be much faster with JAX. So this grad function works with scalar valued functions. So again, this is a function transform. And scalar valued function means that it's a function which maps scalars or vectors to scalars. So let's look at an example. Here we say from JAX import grad. Then here we have a function where we do some computations, and this takes an input. So this can be, for example, a NumPy array or a JAX NumPy array. And then we apply this gradient to the function. This will give us the gradient of f with respect to x. And then we can apply this multiple times. So this will be d2 of f with respect to x. So we could do it like this, or we can simply use this result from the first step and do it like this. So this will give you the same. And then here I execute this and print this. So this is the original function. And now here we call this, and then here we call the first gradient and here the second order gradient. And if you compare this and also do the math for yourself and calculate this, then you see this will be the correct results. So this is how simple you can calculate the gradients by just using this grad function. So here is another function. So this is a little bit longer code where we do, for example, a if statement and a for loop. And here we basically calculate a rectified cube. And notice that here the if statement depends on the value. So this is different than before with chit. So if we apply chit to this function, then it would not work. But for the gradient here, this is okay. And then this is still correct. So now if we calculate the gradient and then again compare the math, then this is correct. So in this example, like I said, this calculated the gradient with respect to x. And if we have a function with multiple parameters, then by default, it will always calculate the gradient with respect to the first parameter. So if we simply call grad on this function, then this will be with respect to x. And if we want to change this, for example, if we want it to be with respect to y, then we can pass in this argnums argument. And here we say 1, so the indices start at 0. So now it will be with respect to 0 to y. We could also put in multiple arguments. So now it will compute both the gradients with respect to x and also y. So this would also work. So now let's run this, and then here we see the results. And yeah, so this is when we want to apply this to scalar valued functions, but we can also calculate gradients for vector valued functions. And for vector valued functions, we can calculate the Jacobian and the Hessian. So vector valued means we now map vectors to vectors, and then the analog to the gradient is the Jacobian. And for this, we can use two transformations, either jac forward or jac ref. This corresponds to forward mode differentiation and reverse mode differentiation, and they should both give you the same result. These are just two different ways of implementing this, and sometimes one can be faster than the other, but I won't go into more detail here for this. Just have a look at the official documentation. But the way it works is that now we import this from JAX, and then here we have a function that maps a vector to another vector. And then here we apply our Jacobian to the function. Then here we create an input and then we call our Jacobian. And now if we run this and compare the result to the actual math, then you should see that this is the correct result. And the way to get a Hessian is by first calling grad and then this Jacobian. And then here again we have an example function and then we apply our Hessian to the function and give it an input. And then again we can run this and compare it to the math and see that this is correct. So yeah, this is how we can calculate the gradients for scalars and vectors. Now let's have a look at another great feature of JAX, and this is automatic vectorization with vmap, which stands for vectorizing map. And it has the familiar semantics of mapping a function along array axes, but instead of keeping the loop on the outside, it pushes the loop down into a function's primitive operations for better performance. So let's have a look at an actual example to make this more clear. So in this example, we have a function where we want to convolve a vector x with weights w. And for this, we have a for loop where we iterate over each element of x. And then here we apply the dot product of x and then the weights w, and then append this to the output. And now suppose we would like to apply this function to a batch of weights and also a batch of vectors. So for this, we simply stack a couple of vectors. And the manual way to do this is to do a simple loop over the batch. So here we loop over the size of the batch and then access all the elements. And then for each element in the batch, we apply the convolve function. So this would work. But with this vmap function, it's actually much more simpler and also much faster. So here we simply apply vmap to the convolve function, and then here we call this and print the result, and here we also print this result. And now if we run this, then the first print statement is the normal convolve. Then here we see we get the same result, but with vmap it's much shorter and much faster. So this is another very useful feature. Then I also want to quickly mention another very useful feature, and this is automatic parallelization with pmap. So with this, we can, for example, do distributed training and distribute our computations, for example, across multiple TPUs, and then it's much faster. And for this, I don't go into more detail. I just want to mention that this is possible with JAX by simply applying this pmap function. So for this, again, have a look at the documentation and know that this feature exists. So these were all the essential features with JAX I wanted to show you. And now the last code I want to show you is a simple example training loop with JAX. So here we implement a simple linear regression model, and now I show you how this could look like with JAX. So here we create some sample inputs for x and y, and then if we plot this, then this is how our function looks like. And now let's approximate this with a linear regression model. So for this, we create a model function where we simply apply the weights times x plus a bias b. Then we define a loss function, and in the case of linear regression, we want the mean squared error. So first we apply the model, which will give us the prediction, and then we call JAX NumPy.mean, and here we have the prediction minus the actual value to the power of 2. Then we also define an update function, so this is important here. So to update the weights, we apply gradient descent. And the way it works is that we start with the theta and then move into the direction of the gradient. So we need the gradient, and then the learning rate basically is our step size. So to get the gradient, we learned this before, we simply have to call the grad function and apply this to the loss function, and then we can move in this direction. And now to do the training, we initialize the values of w and b, and then we do this 100 times and call the update step, and then we get the values for theta, so for w and b. And if we run this, then, sorry, I have to run this cell first. And if we run this, then this might take a few moments to do the training 1000 times. And now we get the result. So for the W, we get 3, and for B, we get -1. And this is how the values looks like if we plot this with our approximated model. So yeah, this looks almost similar to this. So this works, and this is how we can do a simple training loop with JAX. All right, so these were all the things I wanted to show you. This all sounds super exciting. And now let's briefly talk about what's the catch. So I talked about this before already when we talked about the just-in-time compiler. So we need to make sure to follow the functional paradigm. So we need to implement pure functions and have to understand what this means, because otherwise we can get untracked side effects, and this is super dangerous. So be very careful if you want to apply the JIT transform. Then we have to be aware that we cannot modify arrays. And with JAX, we need explicit random number handling. So for this, I also recommend to read this article from the documentation. But basically, we cannot use a stateful pseudo random number generator like with NumPy. And here we have to be very careful when we want to reproduce our results. So if you care about this and random numbers, then also make sure to read this article. But yeah, overall, what's the conclusion? So I think JAX is a very promising project, and it has been steadily growing in popularity despite the learning curve. And it's still considered as an early experimental framework. But yeah, I'm very excited to see what's coming in the future. If you just want to use it as a drop-in replacement for NumPy, then it shouldn't be too hard, and also you don't have to worry about a lot of things. This works most of the time without problems. Then the autograd feature is very useful for scientific computing, also for deep learning. You can get a huge performance improvement, but of course, as I said, you have to understand how pure functions and how this JIT works so you don't get side effects. But yeah, overall, I think it's really cool. Let me know in the comments if you like this tutorial. Let me know what you think about JAX if you want to use it in your projects. And then I hope you enjoyed this tutorial, and I hope to see you in the next one. Bye.